Quantum confinement is a fascinating effect that occurs when nanoparticles are so small, often only a few nanometers in size, that the motion of electrons is confined in all three dimensions. This confinement leads to changes in the energy levels of the electrons, making them discrete instead of continuous, as in bulk materials. Why does this happen? When particles are reduced to sizes comparable to the electron's natural wavelength, the exciton-Bohr radius, the electrons can no longer move freely. Instead, they are squeezed into a very small space, which forces them into specific, quantized energy states. Imagine a guitar string. If you shorten it, the pitch increases. Similarly, as the size of a nanoparticle decreases, the energy gap between these quantized levels widen. This means that properties like color, conductivity, and chemical reactivity can change dramatically compared to larger bulk materials. One well-known application of the quantum confinement effect is in quantum dots. These semiconductor nanoparticles emit light in specific colors that can be finely tuned simply by altering their size. Smaller quantum dots might emit blue light, while larger ones could glow red. This tunability makes them incredibly useful for applications in display technology, bioimaging, and even solar energy. For instance, in display screens, quantum dots provide a vibrant and efficient light source that improves color accuracy and energy efficiency. Another interesting aspect is the impact on electronic and optical properties. When quantum confinement sets in, nanoparticles can behave like artificial atoms, showing discrete absorption and emission spectra. This behavior is not only key to developing new optoelectronic devices, but also provides a way to study fundamental quantum mechanics in a controlled environment. What happens when you alter the size of these nanoparticles? Their optical properties change in predictable ways, offering a powerful tool for designing materials with specific functions. Applications of the quantum confinement effect extend to sensors and catalysts as well. In sensors, the sensitivity can be dramatically enhanced because small changes in the environment can cause measurable shifts in the energy levels of the confined electrons. In catalysis, the altered electronic structure can lead to higher reactivity, which improves the efficiency of chemical reactions. The quantum confinement effect explains how reducing the size of a material to the nanoscale can lead to entirely new properties thanks to the discrete energy levels of electrons. This effect is key to many exciting applications, from vibrant quantum dot displays and efficient solar cells to advanced sensors and catalysts. Could the manipulation of these tiny particles pave the way for even more innovative technologies in the future? The answer seems to be yes, as ongoing research continues to uncover new possibilities in the realm of nanotechnology. Quantum confinement is a phenomenon that occurs when the dimensions of a material become comparable to the wavelength of its charge carriers. At the nanoscale, electrons are restricted in their movement, leading to discrete energy levels instead of continuous bands. This effect dramatically alters the physical and chemical properties of materials compared to their bulk counterparts. Understanding quantum confinement is key to explaining many unique behaviors of nanoparticles. Nanoparticles of the same material can exhibit different colors when their size is varied due to changes in their electronic energy levels. It's like tuning a radio to specific channels. As you adjust the dial, you pick up different stations, energy levels. The quantum confinement effect arises because electrons are confined in a small space, which forces them into quantized energy states. As a particle size decreases, the spacing between these energy states increases. This change in energy levels impacts the optical, electrical, and chemical properties of the material. It demonstrates the intersection of classical physics and quantum mechanics in the nanoscale regime. When the size of semiconductor nanoparticles is reduced, their band gap widens, leading to a shift in the wavelength of light they absorb or emit. It's like having a small room versus a large hall. The limited space in the room forces people to have distinct positions, while in a hall they can move more freely. Quantum confinement alters the electronic properties of nanoparticles by changing their energy level structure. The discrete energy states affect how electrons can be excited, influencing conductivity and reactivity. This size-dependent behavior allows for tuning of a material's electronic characteristics by simply controlling its dimensions. Such control over electronic properties is crucial for developing nanoscale devices. In quantum dots, adjusting the particle size can change the energy required to excite an electron, which is critical for creating custom electronic and photonic devices. It's like adjusting the volume on a speaker. The electronic settings of the material can be fine-tuned for a desired output. One of the most striking effects of quantum confinement is the change in optical properties, particularly the color of nanoparticles. As the size of the particles decreases, the band gap widens, causing a blue shift in the light they emit or absorb. This size-dependent color variation allows scientists to engineer nanoparticles with specific optical characteristics. The effect is widely used in applications ranging from display technologies to bioimaging. Quantum dots in different sizes can be synthesized to emit vivid colors, making them useful in creating high-resolution displays. It's like mixing different amounts of pigment in paint. Small changes in concentration can produce a wide range of colors. The quantum confinement effect leads to size-dependent energy levels, which means that the band gap of a nanoparticle changes with its dimensions. Smaller nanoparticles have larger band gaps, which directly influences their electrical and optical behaviors. This property allows for precise band gap engineering, enabling the design of materials with tailored properties. Such control is essential for optimizing materials for specific applications, like lasers and solar cells. By controlling the size of nanoparticles, engineers can design materials that absorb specific wavelengths of light, enhancing the efficiency of solar panels. It's like adjusting the settings on a digital camera. The right configuration leads to optimal performance for different lighting conditions. Quantum confinement can significantly affect the electrical conductivity of semiconductor nanoparticles by altering electron mobility and energy distribution. The discrete energy levels restrict electron flow, which can enhance or reduce conductivity based on the material's size. This effect is exploited in semiconductor applications to create devices with improved performance and lower power consumption. It forms the basis for innovations in nanoelectronics and quantum computing. Nanoscale transistors benefit from quantum confinement by achieving faster switching speeds and reduced energy loss. It's like water flowing through a narrow pipe. The reduced space controls the flow rate, which can be optimized for efficiency. The tunable properties of nanoparticles through quantum confinement are critical for enhancing energy storage devices and solar cell efficiency. By adjusting the size of semiconductor nanoparticles, the absorption spectrum and charge separation efficiency in solar cells can be optimized. This leads to improved light harvesting and energy conversion rates in photovoltaic devices. Through the ability to control these properties makes quantum dots and other nanomaterials valuable for renewable energy applications. Quantum dot solar cells can be engineered to capture a broader spectrum of sunlight, increasing overall energy output compared to traditional cells. It's like customizing a car engine for maximum fuel efficiency. You fine-tune every component to get the best performance possible. Quantum dots, a type of nanoparticle affected by quantum confinement, are increasingly used in medical imaging and diagnostics due to their unique optical properties. Their bright, tunable fluorescence allows for highly sensitive detection of biological markers. The small size and customizable surface chemistry enable quantum dots to target specific cells or tissues in the body. These properties are transforming diagnostic techniques and enabling early disease detection. In bioimaging, quantum dots can be attached to antibodies to detect cancer cells with high precision, improving diagnostic accuracy. It's like using a high-powered magnifying glass with adjustable focus to examine the fine details of a specimen. Each adjustment brings out a different aspect of the target. Research into quantum confinement continues to push the boundaries of nanotechnology by enabling the development of new materials and devices with unprecedented properties. Future innovations may include more efficient energy conversion systems, advanced electronic devices, and innovative medical diagnostics. The continued study of size-dependent properties will allow scientists to design nanoparticles that meet specific performance criteria. This evolving field promises to revolutionize various industries by harnessing the unique effects of quantum confinement. Emerging research aims to create multifunctional nanoparticles that combine energy storage with diagnostic capabilities, offering breakthroughs in integrated technology applications. It's like upgrading from a basic mobile phone to a multifunctional smartphone. Each advancement adds new features and capabilities that transform everyday experiences.